Continuing our review of class, consider mass on a spring. The equilibrium position will be right here. And the position of the mass will be right here. And the x vector is the vector from here to here, the vector that goes from the equilibrium position to the position of the mass. If we graph the magnitude of F versus the magnitude of X, again, I asked for a choice of these four possible curves, and of course one of them is one that we probably aren't really going to see. So the choice would be between a curve that's concave up, a curve that's concave down, and a curve that's linear, knowing incidentally that the force is zero at the equilibrium point. The curve is at the equilibrium point. The spring is neither compressed nor stretched, so it's not exerting any force in the direction of motion along this surface. Okay. Now, most people chose the straight line path, but there's no good reason, except maybe prior knowledge, to reject either of these other two paths. We really don't expect the force to fluctuate like the wavy path here. And in lab, we're going to attempt to observe, take data to confirm whether the spring does have a force that varies linearly with position. Now again, this is magnitude of X, magnitude of F. The directions of the force, well, obviously if you pull the spring back this way, it's going to exert a force back this way. So the force is in fact going to be opposite. The force exerted by the spring is going to be opposite to the direction of the displacement. And if the spring is compressed, of course, the force will be out this way. And as I say, on an ideal spring, this is going to be the case, and it'll be at least very close to the case for most real springs, as long as they're not too massive. Okay. Now we imagine, because we want to look at the energy of this thing, the energy associated with this system, we imagine that we push the mass from here to here. Just push it slowly. We've got to exert a force in this direction. I should be more specific. The force to push against the spring, because there might be friction here. We can get rid of friction by talking about this being an ideal case where there is no friction. But this is the force that we use to push against the spring, against the force exerted by the spring. And again, we're pushing it slowly, so there's no appreciable acceleration. So the force we exert only needs to be, basically, we give it just a little start and then push it very slowly and then come to a stop, except for that very brief instant at the start, the very brief instant at the stop. The mass is moving at a constant velocity. If there's no friction, then our push is going to be equal and opposite to the force, because if the velocity is constant, the acceleration is zero, so the net force is zero. So my force, spring force, have to add up to zero, so my force has to be equal and opposite to the spring force. Okay, anyhow. And this whole sentence is losing its fluidity. It's the force to push the mass away from equilibrium, force exerted against the spring. Okay. The graph is going to look like this. When I'm pushing the spring in the positive direction, where I'm pushing the mass in the positive direction, I'm going to have to exert a positive force, a force in the direction of motion, assuming the positive direction to be this. And if I'm pushing it back this way, on the other side of equilibrium, remember the equilibrium is where x equals 0, and so there's going to be the equilibrium point. If I pass that point, then I'm going to be pushing in this direction, and the spring will be pushing back in this direction, so I'm going to have a negative force. This is the force I have to exert, not the force exerted by the spring, the force I have to exert. Force exerted by the spring would have a graph that looks like this. It would exert a positive force when x is negative and a negative force when x is positive. Okay, so we're looking at the work I have to do to extend the spring, basically. Let's assume that if this is linear and passes through the origin as it must, if this is the if there's zero, x equals 0 is the equilibrium point, the graph has to pass through that point because there's no force at that point, zero force at that point. Okay. Then, if the graph is linear, it has some slope. So we're going to call that slope k. So the force equals k times x. Now, how much work does that force do between position x equals 0 and position x equals a? Okay, there's the question. And got a pretty quick response that that's going to be the area under the curve. Well, it is, and that's a very good response, but let's make sure we justify it. Okay, in this picture, at first I didn't have this sloping line here, so let's pretend it's not there. If we have a force versus position graph that's horizontal on the top, then over an interval delta x, the amount of work this is going to represent is the force multiplied by delta x. So that the area would be F delta x. Okay, if it's a rectangle. I didn't write that in because it was clear from the context when we were talking about it in class. If we have a linear force of the same nature we've been talking about, whose average force is equal to the force we had in the original rectangle, then the average force is going to coincide with the force represented by the straight line here. So that the force will be F average times delta x. F average in this case is going to be 1/2 Ka. Remember, this is the, okay, if this is x equals a here, then we have F equals Ka here. So that the average force is going to be 1/2 of Ka, and we multiply that by the displacement A, and we get 1/2 Ka squared. So that the area under this curve is very clearly 1/2 Ka squared. Now I've drawn it over here. F equals Ka here. And here's F average. And F average is 1/2 of Ka. So again, confirming this calculation. And confirming that the area under the curve does represent the work done by the force. And I really didn't say it, but the F delta x we get here, or the F average delta x we get for the triangular region, is going to be the work. Okay, the product of the force and the displacement, or the product of the average force and the displacement, depending whether we're looking at this rectangle or this triangle. They have equal areas, equal amounts of work. Okay. Alternatively, we could say that the work done is the integral from 0 to a of the force times dx, the force being kx. If we integrate kx from x equals 0 to x equals a, you can verify that we get 1/2 Ka squared, and you should be able to reproduce this entire argument at any point. It's important that you understand why the force, or why the work done by an elastic force is 1/2 Ka squared, or at least by a linear elastic force. Again, the difference between pulling out a formula that's not that hard to remember and understanding where the formula came from, which gives you much more power, much more ability to solve problems, to design systems, etc. Okay, now one of the main points is that one of the main points of today's class is that I really don't want you to use the equation PE equals mgy. Now, having said that, I'm going to write that as a bad idea, but you're going to do it anyway. Okay? So when you do this, I don't want you to do it with the idea that that's always equal to the potential energy or even the gravitational potential energy. Another expression for gravitational potential energy is negative capital G, capital M, little m over r, which is the gravitational potential energy of a mass, little m, in the vicinity of, let's say, the Earth, whose mass is big M, where G is the universal gravitational constant, and r is the distance of the mass from the center of the Earth, the center of the mass from the center of the Earth. This is another formula that can represent gravitational potential energies. If you're grabbing onto formulas, be aware that you have at least, at this point, 3 formulas to grab onto. Now, we haven't studied gravitation, so you don't know where this formula comes from. It's actually very simple. And you'll see that. It's every bit as simple as this, just a simple integral. Integrating 1 over r squared instead of x, but that's easy to do. So we have formula for elastic potential energy, 2 formulas for gravitational potential energy, and we don't yet have a formula for magnetic potential energy. And as I said in class, that's something we're going to try to develop in lab on Friday. Okay, well, I'll look forward to seeing you on Friday.